Next up is Samir Agarwal, who is one of the current STAR students in the AMP Lab. He'll be talking about approximate queries. This is one of my favorite projects. If I could go back to grad school, this is the project I'd work on. So please go ahead.
Thanks, Ali. Good evening, everyone. Today I'll be talking about BlinkDB. So BlinkDB is an interactive query processing framework that supports approximate queries on very large data. So my talk would essentially be in two parts. I'll spend the first couple of minutes talking about BlinkDB in general, talking about sampling, error estimation, just kind of like giving a brief motivation. And then the second part of my talk would actually be talking about each of these different components of BlinkDB. And then we'll actually tie it back to the Catalyst frameworks, which actually involves rewriting these plans in order to support approximate queries. So the key goal or the key problem that BlinkDB tries to solve is essentially supporting interactive SQL-like queries on massive sets of data. These queries may range from simple aggregate functions, for example, average, count, sum, standard deviation, percentiles. These queries can have filters, group bys, can probably be joined with some different tables. They can have like a nested query structure. And last but not the least, the functions or the kind of computations that you want to do on this data may range from custom user-defined functions or can even be ML primitives, if possible. So before actually I go on and talk more about this interactivity case, let me give a brief intuition of what does it mean or how long does it take to actually process 100 terabytes of data on 1,000 machines. So let's consider a very simplistic query, maybe like a group by or maybe a scan. And for sake of simplicity, let's just assume that we have one disk per machine. So now if this entire data is striped across hard disks, we pretty much incur around half an hour to 1 hour to process this data using standard cluster computing framework. Now, if this data is cached in memory, the cost of scanning this data goes down by orders of magnitude, but you still have communication costs, So the entire query now takes of the order of 1 to 5 minutes. And in this design space, what we are trying to achieve in BlinkDB is essentially sub-second latencies, or latencies of the order of seconds. And in order to achieve this, we cannot even afford to process or even to scan this entire data at runtime. So for this, we actually propose a new paradigm that involves query execution on samples of data. So what does query execution on samples mean? It essentially means that if we have like this table, which probably has some IDs of customers, their locations, and maybe a metric that we are measuring, in this case, the buffering ratio. And I ask this query, which is, what is the average buffering ratio in this table? Now, a standard database would essentially scan each and every tuple from this table and give us an exact answer, which in this case might be 0.2325. What I can parallelly do is I can have a uniform sample from this table and can actually construct this sample in which each row can occur in this sample with a probability. So in this case, with a 0.25 probability, you can have like a particular row represented in the sample. So now if I actually execute the query on a sample table, I get an approximate answer, which is 0.19 in this case. Now this approximate answer in itself is no good because it does not tell me how far is this answer from the exact answer. So in order for this to be useful, we actually have to augment it with an error bar. And this is what makes this answer useful. So now saying that the actual answer lies within 0.19 plus minus 0.05 with a high probability is what makes this answer useful. And a subtle issue is that you can always operate on bigger and bigger samples, get more and more accurate answer with smaller error bars. So the overall point is that sampling gives us a smooth trade-off between execution time, which is directly correlated with the sample size that you operate on, and the error that you incur while you're operating on samples. As you operate on bigger and bigger samples, so as you go towards the right of the x-axis, you incur less and less error by some error function. Our traditional databases are at the far end of the spectrum. So they operate on always the full data and give us an answer with so-called zero error. BlinkDB is designed to operate on the left side of the spectrum, which is to say that it supports so-called interactive queries by operating on small samples of data and quantifying the error. A subtle point to notice here is that our data almost always has a pre-existing noise. And what this means is that even if you think that you're actually operating on the full data set, it is not generally the case. So now it no longer becomes a question of approximate queries versus exact queries. It's more of a question of where do you want to be exactly on this curve. And BlinkDB basically allows you to make this choice. Just before actually deep diving into the BlinkDB architecture and talking about different components, let me just present a real-world example that highlights the utility and the power of sampling. So in this case, this is basically a 10 terabyte data set. And this particular query is executed on 100 machines. The x-axis here represents the fraction of data on which the query operates. So the 1 essentially means it's operating on the full data set, and it takes around like 1,000 seconds. As you operate on 1/10 the data set, your query time decreases by 10x, which is not much of a surprise because most of these queries are IO bounded. But what is really cool is if we look at the errors that is incurred when we are operating on these samples of data. For this simple case, this is an average query, we see that we can basically get a 99.98% accurate answer in just 1/10 the time. Similarly, we can essentially get 99.1% accurate answer in just like 150 at the time, which is essentially 50 times faster. And this essentially is the power of sampling. So what is BlinkDB? BlinkDB is a framework that's built on Shark and Spark. So BlinkDB is not a database. It's built on a database. So it's a framework that allows you to create and maintain a variety of uniform and stratified samples from underlying data. Uniform sample, as the name implies, essentially mean that you can create samples with a uniform probability, and each tuple in your sample has an equal representation, or an equal probability of representation. Stratified sample, on the other hand, means that you can give slightly biased representation to certain parts of your data set. So if there are certain parts of the data set that you're more interested in than others, you can actually sample them with a higher probability and keep them. On these samples, then BlinkDB supports returning fast and approximate answers with error bars by executing these queries on the sample data. And finally, in order to achieve, or in order to have a system that you can use to take decisions, you need to trust these error bars. So the last component of BlinkDB is essentially a verifier that verifies the correctness of these error bars that it returns at runtime. So let's talk about each of these components one by one. So as far as uniform samples are concerned, BlinkDB essentially supports a logical uniform sampling operator that can be inserted anywhere in the query graph. Now, what this sampling operator does is it actually expects a stream of data. This stream is just like a random table that's inputted in this sample. And this uniform sample does like these three things in succession. First, it filters this particular stream of data randomly by tossing like or essentially generating a random number and assigning or basically comparing it with a sampling probability and generating a sample that's 1/3 the size of this corresponding sample. So essentially Bernoulli sampling. Second, it adds per row weights to this random sample. These per row weights are now useful for rescaling the answer back and generating a scaled approximate answer, and also for quantifying the error that's associated with this sample. And finally, optionally, you can also order or shuffle this data, or shuffle the sample that's generated by this uniform sample. And shuffling is important because if you shuffle this entire random sample that's generated, any subset of that random sample is also a random sample. So you can actually get this smooth trade-off between accuracy and runtime. Finally, the sampling operator actually outputs an RDD, or like an intermediate data in Shark, that has this following characteristics. So it is essentially a random sample from this data set, from the original data set, and it has this transparent weights associated with it, which essentially is the sampling weights that are there in the original table. Now, these weights are completely transparent, so they do not change any semantics of the original query plan. If you just insert this like this RDD into various logical operators, nothing will change. It will still compute the exact answer. And these weights are only used to essentially compute the error or scale the answer back. For stratified sample, similarly, we can insert the stratified sample anywhere in the query graph. And what the stratified sample essentially expects is an input stream of data with a set of columns. It can be a single column. It can be multiple columns on which you want to stratify or bias the sample. What the stratified sample does is it inserts a split operator in the query graph which logically splits this data into two streams. Now, one of these streams essentially is inputted into a group aggregate operator, which operates on one of these streams and computes a summary of this entire sample that is inputted. So in this case, we just compute this simple summary that associates a count with every city. So in this, for example, in the original sample, we had 7 values of NYC and 5 values from Berkeley. Now, based on this group operator assigns a ratio to this stratified sampling operator. Now, this ratio is something that's defined by whatever the logic is associated by creating these stratified samples. BlinkDB supports a variety of such logics, but we also allow basically having custom logics in the stratified sampling operator. But in this case, for the sake of this example, my essential logic is that I am keeping 2 rows on average for every strata, that's New York and Berkeley. Now, this is essentially fed, the summary and the original table is joined together on the keys that are being stratified on. Once we do this, we essentially get a ratio associated with every tuple. So all the values of NYC would now be associated with a sampling ratio of 2/7, and all the values of Berkeley would now be associated with a sampling ratio of 2/5. Finally, we just have this corresponding uniform sampling operator in the query graph, which generates a weighted stratified sample from this data. Once again, the weights are completely transparent. They do not interfere with the original execution of the query, and all they do is they just scale back the answer appropriately as the semantics govern. So one thing to notice here is how useful Catalyst is in actually rewriting this query plan. So in both these cases, when we are inserting these operators in the query graph, we can actually just write functional dependencies in order to generate parts of these query plans and do this seamlessly. The second aspect of BlinkDB is to return fast approximate answers with error bars by executing these queries on samples of data. Now, to estimate the error, there are 2 standard techniques. First, you can have something like closed form aggregate functions, which and the sampling error for those functions are governed by the central limit theorem. These closed form aggregate functions are actually limited. There are only average, count, sum, variance, and standard deviation that have so-called closed forms. And they are pretty much simply represented as this. So for these functions, the error that's incurred when you're operating on samples of data is, for example, a function of either the sample size or the variance of the sample, maybe the mean of the sample, and so on and so forth. So for these simple cases, rewriting such a plan in BlinkDB is easy because all you do when you're executing a query on a sample of data for any of these 5 functions is just rewrite the aggregate operator and insert this error calculation module into the aggregate operator. However, these aggregate operators are limited, which is why we need some kind of like a generalized aggregation or error estimation function as well. The generalized aggregation function use a technique such as statistical bootstrap to estimate this error. And this technique is actually applicable to even complex and nested queries. It can be applicable to user-defined functions or even queries that may have joins in them. So all in all, bootstrap, being a statistical estimation technique, is fairly generalized. Now, the key idea behind bootstrap is actually to resample from this original data, and you continuously resample from this original data and then execute the queries on these samples. The answer that you get by executing multiple queries on this sample then give you an idea of the error that's associated with the query. So as far as the plan rewriting is concerned, if you have this particular sample and you have a particular query that produces an answer A, what the bootstrap would do is it would execute on the sample of data, and it would insert this resampling operator in the query graph. What this resampling operator does is it reconstructs this resamples from this original sample, and you have like essentially multiple instances of the same query operating on these so-called resamples of data. Now, statisticians generally say that 100 instances are good enough for computing this answer, but all in all, this is what the query plan looks like. Now, these 100 instances of resample query are then fed into a bootstrap operator that consists of a simple logic that produces this error estimate. So Bootstrap is more generalized, but as you can see, it's more computationally expensive. However, on the other hand, closed forms, which are not so generalized, they are applicable only for a specific set of queries, are fairly easy to compute. Now, both Bootstrap and closed forms are actually statistical procedures, and all statistical procedures operate under an assumption, under certain assumptions of what the query is, what the data looks like, and so on and so forth. Which is why, if you have to design an approximate query processing framework that can actually give you correct error bars always, we need to have some set of correctness verifiers or some tests that can actually tell us whether the error bars that's outputted by these procedures in our context is right or wrong. To this end, I mean, there have been actually research in the statistics community to have these sets of diagnostics that can be applied to a query in order to figure out whether the error that's associated with a particular sample size, as estimated by these procedures, closed forms, Bootstrap, is correct or not. So all in all, what these procedures do is they operate on a particular sample size, look at the error, and what they give us is a thumbs up or thumbs down, whether this particular error is correct or not. And without actually going into the statistical details of the method, from a systems perspective, what these methods invariably do is they operate the query on very, very small samples of data and multiple small samples of data and try to estimate the error that's associated with these very small samples of data. Now, in order to estimate the error using closed forms, you just have a single query. But in order to estimate the error using Bootstrap for complex queries, you again have so-called multiple subqueries on these resamples of very, very small samples. Now, as might be obvious, the research essentially says that the more data points that you collect, the higher is the accuracy for predicting correctly whether the error bars that is outputted by Bootstrap or closed forms is correct or not. Moreover, they essentially mention that around 300 data points is actually resulting in 97% accuracy on some of the data sets that we used. And this is actually, I mean, for closed forms, 300 data points essentially means 300 queries. But for Bootstrap, 300 data points essentially means 30,000 queries. So all in all, if we actually look at an approximate query processing framework that does these three things, that returns an answer, that returns an error bar using Bootstrap maybe, and that verifies whether the corresponding error is accurate or not, we are talking about one query that estimates the answer. We are talking about 100 queries on resamples of data that computes the error. And we are talking about close to tens of thousands of queries to just verify whether this error is correct or not. In order to do all of these and still maintain interactivity, we had to actually re-engineer the entire Spark stack. And for this, we actually had to enable what we call as the single pass execution of this entire data. How this works is that if we have a query, if we have just a sample query that operates on a sample of data, let's say that this sample looks like this. So we have, like, in this particular table, 3 columns, and we have a weight that's associated with the sample. So it's a 25% sample of the original data. First of all, we insert a resampling operator in the query graph, as is the semantics. Now, this resample operator is actually a pass-through operator. So it behaves in exactly the same way as filters. And hence, it can be pushed into the query plan, pushed down other filters and projections in the query plan. What this means is that this resampling operator now operates on a fraction of data. So if we are pushing the resampling operator after all the projects and the filters, the resample that happens without changing the semantics operate on just a fraction of data. Furthermore, now this resampling operator, according to the semantics, need to actually compute multiple resamples of data and then execute multiple queries on these resamples of data, which actually becomes extremely slow. And this is the thing that we want to avoid in a single pass execution. So for this, what we did for BlinkDB is essentially re-engineer the data primitives that are passed through a query. What do I mean by that? Is essentially we use a technique called Poissonized resampling to generate samples with replacement. How this works is, for every tuple that's associated as part of the query, we associate a scaling factor to this tuple. The scaling factor is governed by sampling from a Poisson distribution with a mean of 1. Now, what this enables me is that these set of scaling factors actually govern or is actually approximately equal to a resampled distribution from this data. So all in all, this basically means that this S1 column is the weight that associated with a particular resample that I take from this original distribution. And this is a well-known result in statistics. Now, what this means is that I can actually execute or I can generate these so-called Poissonized weight on each of these tuples, and then without actually having to resample continuously multiple times, I can just associate these weights on parts of my query, on the single query, and generate these answers or generate these so-called resampled aggregates by just in a single query execution. And pushing this argument to its logical extreme, if we have this sample that's in the system, what BlinkDB does is it first of all associates these so-called 100 bootstrap weights to a sample. These 100 bootstrap weights are, in a way, computing the error, computing the resample distribution for the 100 resampled versions of the query. Then it actually adds the diagnostic weights. So recall that the diagnostics actually implement bootstrap or estimate errors using bootstrap on very, very small samples of data. And a subset of any random sample that's shuffled in a data system is also a random sample in itself. So what BlinkDB does is it actually associates these weights to even subsets of the samples in order to run the diagnostics while the query is being executed. So as you're executing every tuple, you are actually executing the query on various resamples of data as well. Now, these resamples can actually be encoded using log n bits. So all in all, we see that essentially you need around 4 bits to indicate the count that's associated with every scaling factor of this resample. And if we have around 400 of these so-called resample numbers, this adds an overhead of 200 bytes to every tuple, which we have seen is quite manageable. Furthermore, as you can see, we can completely parallelize the system. This is embarrassingly parallel because we can operate on any subset of these rows. And if we have our samples across the cluster, we can actually operate on any subset of these rows on any machine and then just integrate or aggregate the data in a single bootstrap or diagnostic operator that makes the decision and quantifies the error. So building on this single pass execution technique, we have actually shown, in this example, what I'm showing is essentially just 5 so-called worst performing queries in Conviva. So we actually conducted our experiment on hundreds of queries, and these are so-called the 5 worst performers. So this is basically the worst case of BlinkDB. In this case, we executed the query on around tens of gigabytes samples, and essentially they were given an error bound of 10%. So they can actually operate on parts of 10 gigabytes depending on whenever they achieve their error bound. The entire query was executed on around 100 machines, and they normally took between 1 to 1.5 seconds to execute. The bootstrap estimation overhead for these queries ran into like around 0.5 seconds. So the additional 100 subqueries on resamples of data just took less than 0.5 seconds. And finally, the diagnostics overhead was around a second. So the additional overhead of running the query on very, very small samples of data just was less than a second. So all in all, what we have achieved is we have actually achieved query response time on gigabytes of samples of data, which are within 2.5 seconds. And this is the worst case. So most of our queries actually complete within 1.5 seconds, within 2 seconds. And the worst performing queries with a 10% error from Conviva actually even took less than 2.5 seconds. Overall, I'll just conclude the talk by showing some kind of BlinkDB architecture slides. BlinkDB right now supports the Hive query processing framework. It also supports Shark, and it also supports Presto. At the bottom, we have this Hadoop storage layer. Then we have the execution engine. BlinkDB essentially makes the corresponding changes, or all its changes, in the query processing framework. So we extend the SQL parser. The red components actually indicate the things that we change. We extend the SQL parser to add support for these sampling-based operators. We extend the query optimizer to rewrite the query plans at runtime. We extend parts of the physical plan, implement certain UDFs, extend the execution plan to just make all these corresponding changes in the system. So as far as the other components are concerned, as far as the execution engine is concerned, as far as the storage layer is concerned, it is completely compatible with the existing frameworks. So if you want to just try it out, we have open sourced and released the BlinkDB Alpha 0.1.1 at blinkdb.org. What this version does is it allows you to create these so-called random and stratified samples on native tables and materialized views. So essentially, you can insert this operator anywhere in the query graph. We support adding basically approximate aggregate functions with only statistical close forms for now. And essentially, there will be soon a release that supports this so-called arbitrary UDFs and other functions as well. And finally, we are completely compatible with Apache Hive, AmpLab Shark, or Facebook's Presto. So in case you're already trying out or using some of these query processing framework, you can just run BlinkDB on top of it and look at how these query trade-off behaves. Finally, if you have been actually following the BlinkDB feature roadmap, two things that we promised like a couple of months ago was actually to add this support for a majority of Hive aggregates and user-defined functions and runtime correctness test. Looking forward, we are eagerly working on essentially integrating BlinkDB with Shark and Facebook's Presto as an experimental feature. We are leveraging Catalyst to actually rewrite parts of the plan in Shark so that essentially you can have like these approximate queries there. And finally, we are working on two different components. One is essentially adding this automatic sample management support in BlinkDB, which is to say that as a user, you should not worry about how samples are created and maintained in the system. As a user, you should probably just associate time bounds or error bounds to your query. And based on these time bounds, BlinkDB should automatically decide whether a particular sample is good enough for executing the query and giving in that corresponding time or error bound. And finally, we are also looking forward to integrate streaming support, which is to say that if you have a stream of data, you can create samples of data and then run ad hoc queries on these streams. To conclude, if there is one thing that I would like to just highlight from this talk is that approximate queries are an important means to achieve interactivity in processing large data sets. And to this end, we are actively working on BlinkDB, which is a system that provides approximate answers with error bars by executing queries on small samples of data. And the way that we are designing the system is that it can run on any existing database, specifically Hive, Shark, and Presto. And it would support these queries natively. Finally, this talk was kind of like hopping around a bunch of places, but in case you're interested more in like the statistical foundations of the project or some systems aspect, please check out our Eurosys and KDD papers. Thank you.
Questions? Any questions? Yeah.
Did you have to make any changes to Spark or Hadoop MapReduce in order to get this to work, or are you usually working with an abstraction level of the database?
No. So we have always basically been making changes in the data layer or the query processing layer. So we have not made any change in the execution engine or the storage layer.
Hi, the numbers that you showed in your presentation, is this coming from boxes or physical boxes or virtual?
So these experiments are on 100 Amazon EC2 M1 large machines. So essentially, these are Amazon instances numbers.
Maybe the next speakers can set up. Yeah. Any other questions? Okay, so I have a question while you're setting up. So these stratified samples, they have to be like on disk, right?
Yeah.
Is it possible to do it on the fly?
Definitely. So in BlinkDB, we are actually in no way constricting the user to have offline versus online sample. Theoretically, you can have like online samples. You can insert the sampling operator, and then all the aggregate operator in that query would just be fed the samples. However, I mean, essentially, there are 3 costs that are associated with the query: the scanning cost, the computation cost, and the communication cost. So online sample would still incur the same scanning cost, but it would reduce the computation and the communication cost. Offline sample, on the other hand, would reduce all 3.
Thank you.
Thanks.